All right, welcome to your review for the nervous system. We're going to do a little bit of a free-form style with this one. So this review is not designed to completely replace your PowerPoint notes. I would encourage you to look over those and any other reinforcement work we did. Again, this chapter is broken down into 4 fairly distinct topics. The first one I'll address is the divisions, and this is pretty simply reviewed. The nervous system consists of 2 broad divisions, the central nervous system and the peripheral nervous system. The central nervous system consists of the brain and spinal cord only. The peripheral nervous system consists of nerves going towards the central nervous system and nerves going away from the central nervous system. Those divisions are the sensory, going towards, and the motor division going away. Sensory division is also known as the afferent, as in affect, and the motor is the efferent, as in having an effect. The motor division is further subdivided into nerves that go towards voluntary components like the skeletal muscle, which would be the somatic nervous system, and nerve fibers that go to areas like smooth muscle or glands, which are under involuntary control, and that is the autonomic subdivision of the nervous system. And finally, the autonomic nervous system is broken down into your fight or flight division, which is the sympathetic division, which would raise your heart rate, drive blood flow to skeletal muscles, and the resting and digesting division, which is the parasympathetic, which would do have the opposite effects. So those are your divisions. The second half of that first PowerPoint was on the neuroglia. These are supportive cells. They do not conduct electrical impulses. And they are not neurons. We mentioned they do divide. So if you get brain cancer, it's in one of these neuroglia, which is often referred to as a glioma. There were 5 subtypes you're responsible for. Microglia. Let's do this. Microglia, which were your phagocytic bacteria eaters. Astrocytes, which are shaped somewhat like stars and use these arms to physically support and anchor neurons. Ependymal cells, which form up like epithelial cells, and they possess these cilia that allow them to circulate cerebrospinal fluid, which they also create, which cushions the brain and spinal cord. Then we have our insulators, the oligodendrocytes, and the Schwann cells. These first 4 are located in the central nervous system, and the Schwann cells are in the peripheral nervous system. That leads us to the third PowerPoint, which is the neuron itself, and we'll discuss those insulators a bit more. So in reference to the Schwann cells, these insulators are not continuous where the oligodendrocytes are. So this would be a Schwann cell, which we know consists of a substance called myelin. This is the axon, which is the primary functional component of the neuron. I'll say it that way. We have the cell body over here. Coming into the neuron, we have dendrites, the input region. The axon is the output region, and we have axonal or axon terminals here. Recall that these terminals secrete chemicals called neurotransmitters. Let's put an NT, which communicate with whatever's on the other side, which could be another neuron or an effector like a muscle. Dendrites, cell body, axon, node of Ranvier. Alright, I wanted to contrast here the axon and the cell body. The axons being myelinated are sometimes referred to as white matter. The cell bodies which are not are sometimes referred to as gray matter. The axons are the conducting portion of the neuron. The cell bodies are the thinking portions of the neuron, if you will, where information is summed via the dendrites. In the CNS, concentrations of cell bodies are termed nuclei, whereas concentrations of axons are termed tracts. And in the PNS, concentrations of cell bodies are termed ganglia. Ganglion is singular, by the way. And concentrations of cell bodies are official nerves. Concentrations of axons, excuse me. Again, if you were to trace the direction of information, let me go switch colors here. So information comes in through the dendrites. This information is summed as a graded potential, as graded potentials, which potentially can add up to, if we hit that negative 55, which will generate an action potential, which is what travels down the axon until you get to the terminals where the message is then converted to chemicals or neurotransmitters. One more contrast of the gray matter and the white matter. Brain versus spinal cord. Again, in the way they're situated in the body and the way they conduct their business, locations of the cell bodies and the axons is opposite. So what you find in the brain, that the gray matter is concentrated on the outside as the brain grows and more cell bodies and neurons are added. Whereas in the spinal cord, the gray matter is concentrated in the interior of the spinal cord. When the brain conducts information, it conducts it through the brainstem to other regions, so that gives you the white matter on the inside of the brain, which is directly connected to the brainstem and then the spinal cord. And the spinal cord, which is in contact with nerves to the left and right, that matter is then on the outside in close proximity to those nerves. So these are opposite. Last but not least is your action potential. And I think I will just illustrate this with the graph and walk you through the graph. So your important numbers to memorize are -70, negative 90, I guess below that, negative 55, this is all in millivolts, and plus 30. So as we said earlier, well, what we said earlier was about graded potential. Actually, let's start with the resting membrane potential. So recall that negative 70 millivolts is the resting membrane potential. A nerve at negative 70 is a nerve that is off or at rest. Dendritic potentials can some and they can fall. But every now and then, you get one that hits that threshold voltage, which is negative 55 millivolts. The voltage would increase from negative 70 to negative 55 due to the influx of sodium. If enough sodium comes into the cell such that negative 55 is reached, this is a key point that triggers the opening of all the other sodium gates in the cell membrane, which then, at that point, the action potential becomes all. Whereas if it doesn't hit negative 55, it's none, if you will. Once I hit negative 5, then it's an all. Then the potential will rise to plus 30. The rest of the sodium gates enter. Sodium continually floods the cell. Sodium is moving in. This phase is called depolarization. Whereas the negative 70 resting membrane potential, we say the cell is polarized at that number. So at this point we've depolarized. That extreme change, that change from negative to positive, now causes the potassium doors, which have been closed this whole time, to begin to open up. This moves potassium in the opposite direction, which, remember, that pump is very important. That creates that original concentration gradient, which is going to determine which way these ions move once we open up the doors. So once I open up those potassium doors, potassium flows out of the cell, which returns the potential to a negative state. So potassium moving out. This is called repolarization. The membrane continues to repolarize as the potassium doors, we mentioned, just move a little bit more slowly than their sodium counterparts. This period is called hyperpolarization, when the membrane achieves a voltage that's below, less than the resting membrane potential, which is minus 70. Slowly, as all the doors closed, we can place it, I guess, at the bottom of this graph. So at this point, we would say all doors closed, and the sodium-potassium pump continues to chirp away there and bring that potential slowly back to RMP. The other components that were added here, and I'm not sure how to use a highlighter, were the refractory periods. Recall that depolarization is triggered by sodium doors opening. And that's in essence what the trigger for the on state of the neuron. So what you have in the absolute refractory period, when all your sodium doors are open, you would say somewhere right around that threshold to pretty much the top of the graph. At that point, all the sodium doors are open, and you would say you're in the absolute refractory period. Then, as soon as they open, recall that the sodium doors begin to close rather quickly. So, once the sodium doors are closed, you can trigger them to open up again prematurely, but it's harder to do so because in this phase, from the time those sodium doors are closed until where we said all the doors are closed about here, the potassium doors are open. And potassium is flooding out, which is working against what you're trying to do with the sodium. So this creates the relative refractory period in which the cell membrane can be triggered to initiate another action potential, but it's harder to do so because of the movement of the potassium. Good luck.